Let me share my screen. Just one second. Can you see my screen? Yes, no, please.
Yes, sir.
Okay, good. Okay. So let's wrap up with distance vector routing. And I think there will be small amount of material left in routing for now. So somebody sent me a mail yesterday, which is nice. So let me just quickly explain this thing once more with a picture. Just one second. Just give me one second. Okay. So suppose this weights are 1, 1, 1. Then C among other entries will have an entry like this. Destination A, next stop is B. Distance cost is 2. Okay. It cost could have been anything. Right. So this difference, so with split horizon, okay, C sends D this AB2 because this has to propagate. Actually sends not AB2, just A2. Kind of saying that I have a path to A of cost 2. The next stop of C is now importance to D. D, if it accepts this path, will set its entry to AC2. Okay. C does not send A2 to B. So this is what split horizon is. Basically, since B is the next stop on the route to A from C, C does not advertise the same route to B, because what will B do with it? B will have to add 2 plus 1, 3, but it already has a route of 1, so it will not change anything. So it's a redundant information. With Poisson reverse, okay, C sends D A2, okay, and C sends B, it will send A infinity. Okay. So it doesn't, it's not that it does not send anything, okay. It will send the route, but it will poison the route. That is what it is. The reverse route is poisoned, and basically it puts an infinity in this. So infinity means B cannot, or it won't affect the route at B. So normally when everything is up, this is what will happen. Okay. If this link goes down or even the cost increases too much, okay, then B will not try to, in both cases, B will not try to route through C, because in first case it's silence. So B does not even know that C has a route to A through itself. Okay. And in the other case, B knows there is a route, but the route is infinity. Sort of that means no route. So both. So this is what is the difference between split horizon and Poisson reverse. What they do. Okay. Both serve the same purpose. So purpose of both purpose is B should not try to route through A, through C for destination A. Okay. Even if this link breaks, this AB link breaks, okay, We can try to find other routes depending on the topology, but we should not try to route through C, because the route that C knows to A is through B itself. Anyway. Okay, so that is the difference between split horizon and Poisson reverse. But then why do we have two of these things? Both of them, so both can break this two node routing loop. Okay. What you should try to do, again, this is as I've sent the mail, it's not in the exam. So it's your choice whether you want to do it now or you want to come back and recapitulate after the exam. Okay. Try to form a loop with 3 nodes, 4 nodes, and so on. Actual sequence of operations. As I said, it's very much dependent on the timing of things as to when whose routing tables reach which nodes and so on. Okay. As we have seen in the split horizon case, if the infinity propagates fast, then the infinity will wipe out the everything, and which is what should happen. But then if the infinity gets wiped out because the other side's routing table comes first, that's when you have a routing loop, the counting to infinity problem. Okay. One small thing, so that's split horizon and Poisson reverse. One small thing to note, as I have noted here, so far we have said that send the routing table to all the neighbors, send the routing table to all the neighbors, and so on. But routing table entry, let's go to the next slide. So routing table entries are of the form X, Y, Z. Okay, so this is a cost, this is the next stop, this is the destination. So, but when a node sends to its neighbors, it sends only X and Z. Because this is for A, it is important to know who its next stop is. If it sends to some node B, okay, and B does accept this route because it's a lower cost route or whatever, okay, then the next stop is automatically A. So it will actually put X, A, Z in that case out of Z plus something basically, as we have noted. So when you send, even though we have said send the routing table, send the routing table, each routing table entry has at least these 3 fields for now. Okay, it sends only the destination and the cost. The next stop field does not need to be sent. This is obvious. Okay, and this difference between split horizon and Poisson reverse will come. So, what is the problem? So, what are the 5 different things, goals that we had? Remember, we had correctness. You should find the correct route. Optimal, you should find the shortest cost route. Okay. We wanted efficiency, low overhead. Okay. We want robust. That means if there is a change, the routing table should be rebuilt properly. And we wanted, what was the 5th one? This was robust. Okay, fast convergence. Not just robust, but how fast does it converge back to the correct routing table? So, if the network doesn't change, it is obviously correct. The network changes, no protocol can be correct. Okay, if things are changing, you still have to give it some time for it to stabilize. Okay. Optimal distance vector, yes. What do you think? Robust, of course, yes. Okay. Once a link changes, fine, you are counting to infinity and so on. But if you set a proper value of infinity, okay, eventually it will be detected and the correct table will be formed. Okay. What about efficiency? Do you think it is? So efficiency deals with what is the overhead, okay? Which means to build the routing table, kind of how many messages did you have to send? Did you send a lot of messages, low number of messages, how many messages? So do you think it is proper? Low overhead or high overhead? I know we have a very small number of people in the class today. Let's try to be a little bit more interactive if possible. So do you think it's low overhead protocol or high overhead? What will you call it? What is your feeling? Anyone? So overhead is again, what is the number of messages you are sending to build the routing table? Anyone wishes to try? Make a guess, make a guess. Do you think this you are sending a lot of messages? Very low number of messages? What is it?
I think it has high overhead
Okay, why do you think so? Good. Why do you think so?
because it is sending the paths information.
What is that? Path information meaning?
Z.
Z, yes, the cost information. It's not because of that exactly. Okay, it is sending that information. Some information you have to send anyway. But you are right, it is high because in the form that we have said, okay, keeps on periodically sending, I'll say messages, basically the routing table. So you think of it this way, that even if nothing is changing, okay, you have a stable network, no links weight is changing, no links are going up and down, no new link, nothing is getting deleted. But distance vector routing will still keep periodically sending the table out to its neighbors. Now they will also compare. Nothing will happen. No changes will happen because they have already stabilized the correct routes. But by virtue of the nature of operation, distance vector will still keep on periodically sending this messages. Ideally, I want if there is no change, nothing should be transferred. Ideally. Okay. So what can you do? Can you think of any optimization? You get the problem, right? So just think of very small 4-node network, okay, and nothing. So this is 1, 2, 1, 3. And then after some time, as we have noted, all the routing tables will be built properly. And as long as this 1, 2, 1, 3, these weights don't change, the topology does not change, none of the routing tables will change ever after they have been formed correctly. But then distance vector will keep on, all these nodes will keep on periodically sending their routing tables. That is the destination and the cost of all the route entries to their neighbors periodically anyway. All these messages are overhead for nothing. So can you think of this small network and can you think of an optimization? These are again this optimization that I'm looking at is kind of very standard thing to do in many other contexts. But then it has a loophole of its own that you have to be careful about. So think that after the routing table is built, think of this node A, okay, B, C. A was sending its routing table to B and C all the time. So it's sending the same routing table to B and C all the time. After the initial some rounds when the routing tables have been all built properly. So what can it do? Anybody care to try? So can I do this? Can I say that A will transmit only the changes to its routing table? So it will periodically transmit a message, okay, but the message will not carry the entire routing table. It will only carry whatever has changed since the last time A sent B the routing table. So this message from A to B will not carry the entire routing table. A knows what it has sent to B, and then next time A will only send whatever has changed since then, because it says that last time I've already sent you already know this. This is what has changed. If nothing has changed, it will just send a hello message to indicate that it's up. That's it. Can I do this? What do you think? Come on, tell me something. Yes, no. Do you think it will work? This will reduce the messages, right? Because eventually, once this becomes stable, everybody will just send an empty message, just to indicate that they are up, but nothing new to report, rather than sending the entire periodic table every time. Do you agree? कुछ बोलो यार. Can you hear me?
Yes, sir. Yes, sir.
Okay. Okay. So this should work, but this is a problem. And this is, as I said, this is beyond this. So this is very standard techniques when you have to send information to reduce the message thing. You kind of send only changes from last time rather than entire thing. Okay, only incremental things you send. Very standard technique in building many distributed systems. But then there is a small problem that you should be careful about. So let's say A sends B the table, okay, full table, okay, at t equal to 10, and then at t equal to, after whatever the interval, okay, whatever change, just the increment. Do you see any problem with this, or should something that you should be careful about? In certain cases, this may have a problem. The problem is, what if this is lost? So A thinks that B knows the full thing and only this increment would do, but then B only gets this. So it applies this increment over what it has last time you sent this full table. So it will again depend on the type of connection you have, whether you have acknowledgement or not, etc., etc. TCP, UDP, all those things. Because all these protocols will eventually be sending messages over the same Ethernet, same IP that we have seen. We will see Ethernet and all, and therefore it will, again you have to worry about whether it's reliable, unreliable, and so on and so forth. Okay. So problem can be lost updates. So a compromise is basically, if you're worried about the message size, is to send the table periodically, the entire table. And then for some time after that, send only the increments. Now, something may get lost, an increment may get lost, okay? Your table may get lost. But then if you keep on sending periodically, for some time your routes may be bad, but then eventually the routes will again come back. It's a trade-off between the, how fast do you want the routes to come back to normal versus the number of messages, the overhead that you have to send. Okay. Are you with me? Yes, no, please.
Yes, sir.
Okay.
Yes, sir.
Okay. Fast convergence. Do you think it is fast convergence or low convergence? See, if a weight changes, if a weight goes down or a weight changes, cost changes in one link, do you think the rest of the network will converge back to? So convergence means this. I have this graph. Let's say this link goes to 5. This will affect some of the routes. Okay. So how fast does if you look out at the observer on this thing, there are messages being exchanged and so on. Everybody is updating their routing tables. How fast do you come back to the proper routing table at all nodes for this new set of weights? Okay, this can be a change in weight. This can be a link going down. I may add a new link here. That may change the routes. Okay, but if I make a change, how fast does the change affect the routes, and the routes are recalculated properly? whatever needs to change based on the new topology, weight, and so on. Okay. Do you think it was fast convergence? No trick question. Don't worry too much. Just make a guess. What do you think? Is it something that's going to? So think about. I'll give you a hint.
No,
Yes. Somebody was saying something.
it converges.
Your voice is breaking.
So right, converges slowly.
Yes. Okay. Classic example, as we have said, that if you look at this one, okay. So there is a path from A to this, and this is the only path. Okay. A to B. Here, all these intermediate nodes are there. Okay. So if it changes, if this thing changes, this changes the route of this to this, this to this, this to this, this to this to all of them. Okay. But then only after first period, this will come to know. This will come to know it almost immediately. After first period, this one, second period, this one, third period, this one, fourth period, this one. So we say, so this is slow convergence. Okay. So basically, change propagates slowly. How slowly? As we have noted, basically, in the worst case, the diameter of the network proportional to the diameter of the network. Okay. So it's correct, optimal, robust. Overhead is high, convergence is slow. Okay. And you understand that if this chain becomes, if the network becomes large, more number of nodes, okay, then the diameter may go up because everything is obviously not directly connected. Okay. And then this convergence time will go up even more. Okay. So good for, and there was the counting to infinity problem also. So good for small networks. Everything we are saying is good for small networks. So what happens to the large networks? We'll see. Okay. So how can we, so what are the parameters that will affect this convergence time? One is this size of the network, okay, the diameter of the network. Is there any other parameter that affects the convergence time? What do you think? We'll see systems courses. You will, you should keep an eye on it. You have very good teachers for OS. Okay, in my opinion. So you should keep an eye on the design part of it. In systems course is all about design, trading of parameters, and so on. So what is the other parameter? One is the length of the diameter, the maximum distance between two of them, and so on. What is the other parameter that affects your convergence time based on what you learned about distance vector so far? So as I said, this change will propagate after first period to this, then this second period to this, third period to this, fourth period to this, fifth period of this, and so on. So length of the path into number of periods. So what is the other parameter? Other than the length of the path. It is the duration of that period. How often do I trigger the periodic update to my neighbors? As I said, typical for one particular routing protocol is typically around 30 seconds. The 30 seconds and a path of length 5 will take around 2.5 minutes to converge for this information to propagate. But I could have very well set it to 5 seconds. It will converge in 25 seconds flat. Right? So why don't I set it to 5 seconds? Why do I say 30 seconds? Anyone? If I send you my updates more often, obviously you will come to know about the changes faster. So why don't I tell you my updates more often? It's an obvious answer. Because the overhead goes up, then you're sending more messages. So I'm telling you again, this is a very small class, but I can see that some very good students are there. Okay, and I hope the other people at least listen to the lectures, recorded lectures. Okay. But you see, system design is about parameters. You can mug it and say RIP has a period of 30 seconds. But it's very, I will not set a question saying what is the periodic update time of RIP protocol. So then you learn nothing. You just mug some information. You need to understand very simple, obvious trade-offs, as you can see from this discussion. But you have metrics. You have to understand the parameters that affect those metrics, the trade-offs, and so on. 30 seconds is something that people have said based on certain things. I'll discuss later on when I do TCP, when more parameters come and so on. But think about, when you design, basically think about what is it that you're trying to achieve. Those are your metrics. Metrics will be kind of contradictory to each other. You try to improve one, the other will go down. So what are the parameters that affect it? How should you set those parameters? There is no hard and fast good answer, great answer. It will depend, but there are ways of thinking about them. Okay, so my last question to you, I will not expect an answer here, but you should think about it when you come back from your exams. Okay, but this is a good question. So I asked you if split horizon and Poisson reverse does the same thing. They do it in a different way. One is by keeping silent. I'm telling you, by keeping silent, I don't have a route. I have not told you about a route, so I don't have a route. Whereas Poisson reverse says, I'm telling you I have a route of infinity, which is basically telling you that I don't have a route. But both of them are kind of saying that I don't have a route. So why have these two methods? Why not only one? I'll give you a hint. Okay, it has to deal with this thing. Okay, so this periodic sends always full table, okay, or sometimes full, mostly, I have not used was mostly incremental. So, okay. So the answer to why you have this, which one should be used when, why you have these two methods of split horizon and Poisson reverse, has to deal something with, do you always send the full table or do you only send increments? Okay. And the answer, if you think for some time, it's kind of easy. Okay. Just try to apply both of them to both these cases and see what you come up with. Okay. You don't have to do it now, but please do this, and then you will kind of understand split horizon and Poisson reverse. Okay. So this is what we have already kind of did. Advantages of distance vector. Let me just go through the slide quickly anyway. They are simple to implement, low memory requirement at each node. You just keep a simple routes basically. Nobody knows the complete network information. Nobody keeps the complete network topology. Okay. Disadvantage is slow convergence. So it is not just becomes inaccessible, okay, but link weight changes. Okay. As I said, it's proportional to the diameter of the network. Update sent even if no change in routing table. So nothing sent will be interpreted as link failure. So you always have to send something periodically. But then question is whether you send the entire update, rather the entire table, or you send the incremental table. Just what has changed since the last one. Okay. But then again, if things keep on changing, then you have a problem. And then you have this counting to infinity problem, which means you have to set a value of infinity, which means you limit the size of the network infinitely. Other than the overhead part of it, the diameter part of it, the counting to infinity means to stop that loop once it has happened. The only way to stop it, somebody to realize I've reached infinity. I have told you one definition of infinity when you have the cost as the number of hops. Okay. The other means if you can get some other definition of infinity with your cost, that's also fine. But then it will go up to that level. And if infinity is very high, it will take longer time to go up to that level, which will basically again means that convergence is true after a change. So convergence basically means after a change happens, how fast does the routing tables come back to its correct value? Okay, as we have noted earlier. So distance vector routing, nice protocol. You will see it in practice. It will be used for small networks primarily for this reason. Okay, but as we have noted, there is a variation called path vector. Okay, so it increases the message sizes because you don't just keep the cost and the next hop, you keep the entire path. Okay, and you just don't send the destination and cost, you also send the entire path. So routing loops can be detected very fast. Okay, anybody adding itself to that path will just check whether it has already occurred in the path. Again, path vector is not in your syllabus, but know that this is what the variation of distance vector is. Maybe if we do BGP, we'll come back to path vector. Okay, so that was distance vector. And the other big class of protocols is called link state protocols. Okay. And this is kind of very simple protocol. Again, but then you see the big difference. So distance vector was kind of distributed. I only know about my neighbors, and the neighbors tell me something, and based on that I updated it. So I know that these are the nodes that are reaching from me, and I can reach node X through my neighbor A, my node Y through my neighbor B, and that's the cost. But I have no clue in distance vector routing about the network, the actual topology of the network, which links, what weight, and so on, beyond my neighbors. Okay. Whereas in the link state protocol, basically every node will collect the entire topology information. So each node, to do that, each node will have to send this information about its neighbors. And the way it does it is do flooding. Okay, there's something called link state advertisement. So we look at an actual protocol in slightly more detail when we do IP. Okay, the actual protocol that do link state routing. Okay. So basically, if I have a network, whatever the network is, okay, whatever it is, okay. So each node will first send the information about it. It says I have a link to this, I have a link to this, link to this with this cost. So this will send a message and will flood this. And we know that by flooding, everybody will eventually get it. Okay, as long as one path is available to them. If you're disconnected, you cannot do it. So everybody flooding this. So eventually, everybody gets the information about the entire topology. Okay. And once I have the information about the entire topology, I can just locally run Dijkstra's algorithm centrally. Okay. And I can compute the path space. So eventually you get the same routing table. The form of the routing table has not changed. Eventually you still want basically destination. What is the next one that I would send to? Because you cannot send beyond your neighbors directly anyway. And what's the cost? It's the way you are computing that routing. So link state collects the entire information, okay, and then computes like does, everybody runs Dijkstra's locally to compute the routing table. Okay, slightly wrong out here. So it's the same thing as the optimization. So initially you will send everything, okay, but after that you will only change if some link information change, because you understand that after this has sent flooded this to everybody, if this link goes down, okay, so that change has to be provided to everybody again. So you will just keep on monitoring the links, and if this link goes down, it will now send this information saying that okay, this link is broken. Again, it will flood the information. So everybody will eventually come to know this link is broken, update the topology, run Dijkstra's again, and then change the routing table if necessary. So that's the basic idea. So big difference is distance vector, only local information, only neighbors information. Nobody knows the entire topology, and periodically updates. Link state information sends the information at the beginning, and we'll see later on also periodically in the middle, but not as periodic as distance vector. And then when something changes, send it again. But then these sendings are all by flooding, not just to neighbors, to everybody, which means it creates a lot of messages out there. Are you with me? Yes, no?
Yes, sir.
So, correct? Yes. Eventually, everybody will know the entire topology, run Dijkstra, they will get the correct output. And if changes happen, then also the same thing will probably. Optimal, yes. Efficiency, we'll see. Okay. Robust, yes. Okay. Convergence. So now you have kind of a fast convergence, because moment that you know something changes, that node will flood it. You cannot help the diameter thing because it's a network, it will have to propagate. But it does not wait for the periodic update or something. Okay. So it will just change in that thing and it will converge fast. And there is no counting to infinity problem. Okay. What about the efficiency? What do you think? High overhead or low overhead? Well, it depends. Okay. So initially everybody floods to everybody. That is more messages than distance vector. Okay. When you have the topology. But once the routing table is made, okay, if nothing changes, there is no message exchange at all, theoretically. We'll see practically, still periodically we'll send some information, but theoretically, the way link state protocol works, okay, if there is no change, you don't send any further messages. Okay, so I will use the word good. But if there is a change, then again, there is going to be a lot of flooding. Again, the flooding will happen. So if there's a lot of changes, there is a lot of message exchanged. But if just to build the routing table from a stable network, okay, initially there will be some messages, lots of messages, because everybody will flood. Okay, so initially, what is the number of messages? If you had n nodes and e links, what would be the number of messages? Order what? So think of a network starting, everybody's routing table is empty. So everybody will send their neighbor information to all nodes and it will be flooded. What is the number of messages?
N square.
Because each flooded message, there are n nodes flooding. In flooding, each node will go to order e edges. Over every edge, it will go twice. Okay, so n square only if you have a sparse network. If you have a dense network, it can be n. Okay, but after that, if nothing changes, then there is no. For every change, you will again trigger an order E messages, basically. So there are pros and cons, but again, storage large compared to distance vector, as all nodes store entire topology. Okay. So again, good for small networks. Okay. I put it in a code for some reason. We'll talk about when we do the actual protocol. Because see, I'm saying distance vector is for small networks, link state is for small networks. Okay. And these are path vector is just a modification of distance vector. Okay. And these are the major techniques for creating the routing table. Then what happens to large networks? Internet, how do you route in the internet, basically? So we'll come to that question later on. But remember what is distance vector, what is link state, and kind of the parameters, goals, their trade-offs, pros and cons between distance vector, link state, and so on. Okay. Okay, with that, we come to the end of routing. Okay. As I said, we'll look at both one protocol in actual IP routing using distance vector. We have almost covered everything regarding that in this discussion. And we'll look at a little bit about one protocol doing link state routing also. Each of them have books about them, but then you just need to know some facility about it. But the basic techniques, as I said, remains the same. We'll just give you some more details of link state because we have not gone through that in too much detail. So basically link state is this: send the entire network, flood it, run Dijkstra's, create the topology, create the routing table out of it. Okay, are there any questions on routing? Again, exam is still just before routing. So this means this set of slides which I will upload today, okay, it is till the end of the part on packet switching. Okay. So this set of slides I was covering since last week. Part of it is included, but the part that talks about routing, that is not included in the exam next week. Okay, if not, we'll go to start with the next topic. It's kind of easy, or the part that is not easy. The parts that I will do is easy. Today, at least. Well, easy and is a relative term. Just give me a second. Okay, so we looked at Ethernet. Okay, data link layer and Ethernet. We talked about Ethernet frames, their formats that will carry the data from higher layers and so on and so forth. Okay, so what are the higher layers? So we have TCP/IP networks. The obvious two things that we have to talk about is IP, TCP, UDP, and so on. So Ethernet was at the data link layer. Next is the network layer. We have already started talking about the network layer because routing, as we have noted earlier, if you recall, is the main functionality of network layer. So these routing protocols are basically network layer protocols, basically building the routing table. So two main functions of the network layer are routing, is building the routing table, and forwarding, which is actually using the routing tables to forward the packet. But once again, let me caution you that even though technically these two terms are distinct, okay, you will hear very commonly route a packet, which basically means forward a packet. But that's okay. That's commonly we say route, create a route and so on, send it around the route and so on. Okay. So route a packet, you have to understand from context whether routing is talking about building the routing table or routing is talking about actually forwarding a packet using a route that is in the routing table. So the protocol that runs at the network layer is called IP. Okay. So basically your data unit from TCP will be encapsulated in IP, and then IP will be encapsulated in Ethernet, and then set. Okay, I'll talk more about it after we do a little bit. So IP is the Internet version 4. I'm sure you have heard of IPv6 also. There's a network layer protocol in the TCP/IP suite, just for one. And as I said, for every protocol in the Internet domain, okay, there is what is called an RFC. So IPv4 was originally defined in RFC 791. If you just type RFC 791 in Google, you will see. Then there's a lot more other RFCs out there. Okay. So RFC, as we have said in one earlier class, is called request for comment. So whenever you propose a protocol, okay, in the net, TCP/IP layer, this is what we call Internet protocol. Okay, and you want people in the community, the main people running TCP/IP networks to actually run those protocols. Okay, you cannot have an untested protocol run, everybody run it, and then have a lot of bugs and bring down other machines and so on and so forth. Okay, so you have to, there's a IETF, this Internet Engineering Task Force, and you propose it as an RFC. And I said there are ways to write an RFC. There's an RFC for writing RFCs and so on. But it's like a document which describes your protocol in detail. And it's not just English words, it's English words plus exact message formats, who will do what, and so on. So at least one protocol, say you do FTP, have done a little bit of FTP, HTTP, etc. Okay, just go take a look at RFC. So you say HTTP RFC, and you will find an RFC for HTTP and see the level of details that is there. Okay. And then request for comment, it's called request for comments, because then the Internet community, the IETF body, once if it feels that the protocol has merit, say some initial scrutiny, not anything will go out to the public, will put up to the public for their comments on this. So that's where the name request for comments came. So it will stay there for I think there's duration some months, 5 months or 6 months or something, where people will look at it. Some people may implement it. Okay, look at their experience, local implementations, and they will comment on it. And if it passes that comment, then there is a process called it being made an Internet standard. But many things do not formally get recognized as Internet standard, but get adopted anyway. So if you look at an Internet protocol, okay, and you have to implement it in practice, not in the class environment, but then anybody in the world will want to use it. You are building an FTP client that you want anybody in the world to use. You are building a new browser, that's HTTP client. Okay, you are running a new building, creating the code for a new HTTP server, not just installing an HTTP server like Apache or anything basically. But you are writing that code. Okay. So then you have to conform to the protocol standard, and the definitive place to look at the protocol standard is the RFC. Okay, you have to conform to the RFC. You cannot say, I implemented this because that book by that great guy, very well-known person has said it to be implemented like this. Fine, it's good to read those things and so on. Okay, because they usually will give you a nice, good idea and so on. But when you have to implement things and you have to conform to standards for Internet protocols, you say this implementation is compliant to RFC in certain sense. Or the implementation of this protocol is compliant to RFC. Okay, so the RFCs are extremely important. Internet protocol is connection. Okay, something from this machine to this machine. We'll see how we identify machines in Internet protocols. Now we'll come to more specific things. Okay, rather than just talking vaguely about nodes and machines and so on. Okay. But once we have to connect them, there is no explicit. At the beginning, it gets a packet, it sends a packet. It gets another packet, sends a packet. Okay. So it does not try to establish any sort of connection with the other side, as opposed to the TCP that we have seen, okay, where you first establish a connection and then you send the data along that connection. Okay. So it's a datagram oriented connectionless thing, which means it's datagram oriented, which means that each packet is handled independently, sent along its way, and these packets may follow different paths. That is possible. Okay, and connectionless, which means before it sends one packet to this, it does not do anything else. There is no separate connection establishment or termination phase. It just sends the packet out. And then we'll see what happens as it goes on. So it will just look up the routing table, look at that packet, look up the destination address, look up the routing table. If there is an entry for it, it will say, oh, destination is this. Here is the entry. Here is the next stop. Send it to the next. That's it. It doesn't even know where the end destination is. It will just blindly look up the routing table and send it off along its path. Then the next stop will do the same thing to its next stop will do its next stop, and so on. So that's what we have discussed, the process of forwarding using the routing table. So the entire thing that you want to send is broken up into packets. As I said, this data units that are handled at different layers are called differently. At the data link layer, we call it a frame. Okay, at the network layer, we call it a packet. Okay, and these packets are switched between routers, and I had a header to it. So it's just the same packet switching thing that we have talked about. I will break up the data into packets, add a header with each thing, and then this will go through the routers. Routers will decide which path to follow, and this eventually will get to the destination. This is a packet switched datagram oriented approach. Okay, so packets plus header switched between routers, as we have seen. Datagram oriented, which means each packet is handled independently. Okay, nothing before, nothing after. Get the packet, look up the routing table, destination, next stop, forward to the next stop. As simple as that. Main issues handled is routing, okay, which is both building routing table and using the routing table, the forwarding. But we'll see some confusing things here later on in this building routing table part. But again, we'll employ one of the protocol distance vector, link state, etc. to build the routing table, and then in the network layer, when the packet comes, I'll use that routing table to forward it. And then there is something called fragmentation and reassembly, which we'll discuss later on. So you have to remember, IP is an unreliable best effort service. So kind of have a kind of view with it. Okay. So think of earlier we had Ethernet only, and we saw if I give the Ethernet a frame, how does the Ethernet, okay, send it to the other side, and then you have an Ethernet layer here. It makes it pop up the other side. Okay, you do all those things about framing, then encoding, putting the CRC and all those things. Now you have gone one level higher, and I say that if I give you a packet, okay, whether it's broken up here or outside, don't worry. Okay, then basically it says it will try to send the packet and it will try to make this packet pop up here. But just like the Ethernet frame was unreliable service, okay, things can get corrupted. If the CRC check does not match at the receiver, it will just drop the frame. Okay. Same thing if I look at the IP to IP communication, okay, it's an unreliable communication. Packet may reach, packet may not reach. So what is called the best effort service. The standard term for IP is a best effort service. Your network will try to deliver your packet, but your packet may not reach the receiver. So packets can be lost, can be duplicated, received out of sequence. Okay, they can be lost because the underlying frame can be corrupted, for example. Duplicated because, as we have discussed in the lab yesterday, okay, for some reason things may time out and then you may send it again. But IP will not do all that. IP will just send one packet, forget about it. That's it. IP does not do any retransmission, nothing. That's the job of the higher layer protocols that uses IP. Okay. But for whatever reasons, IP does not give you any guarantee what will happen. It will just say, I will make a best effort service to deliver the thing to destination IP address. It may reach, may not reach. For whatever reason, more than one copy may reach. If you send two packets, they may reach out of order. Okay. So when you build protocols on top of IP, you'll have to remember that that's the service that you're getting from it. Okay. And then, as we have noted in that layering thing, what will happen is you will have packets, you will put an IP header on it, then this entire thing, IP header plus data will be passed to Ethernet, and then the Ethernet will put its own frame header on top of it, then the entire thing will come to Ethernet here. It will remove its frame header and then pass the entire thing, the IP header and packet up to the IP header. And then the IP will process the IP header and decide what to do with that packet. We will see some details of that. So we'll come back to this flow of packets a little later. All right, so now we stop talking about things about nodes and machines and so on. Okay, fine, we will talk about them. But how do I identify them? We identify with IP address. You all know that. Okay. So one thing, even I say each host is connected to the internet, identify the unique address, it's actually each network card. Okay. So if you have a router, okay, you have two network cards, or even your laptops, for example, or your desktop machines, many cases. Okay, depends on what interface you have. But you have a LAN connection and you have a wireless connection. Okay. And on your Windows machine, for example, if you open a command window and you will say ipconfig/all, okay, you will see all your configuration network. Suddenly you will see two different IP addresses, one for the wireless, one for the thing. You will see some other things, loop back and all those things, don't worry about them. But at least you should see two if you have both a wireless enabled, okay, actually connected, and a LAN cable, LAN interface enabled, basically, the wired interface enabled. Okay. And actually connected. It has to be actually connected, otherwise you don't have a LAN. Because here we have DHC in most cases. Okay. And an IP address, as you know, is actually 32-bit quantity. We write here as 100.200.300, sorry, 50.6 or something like this. It's dotted decimal notation, as we call it. Okay. But basically it is, you know, these 4 octets just separated out there. So it's actually just a 32-bit integer. Okay. So your 10.100.5.7 is the bit pattern for 10, followed by bit pattern for 100, 8-bit pattern, 8-bit pattern for 5, 8-bit pattern for 7. Whatever the entire thing is, that 32-bit quantity is actually your IP address. So internally, when your network stack processes it, it processes that 32-bit quantity. Okay. Dotted decimal is just, you know, your nice way of remembering and doing something else. Not just remembering, but doing something else. So this is kind of the new thing for you. If you look at this thing, okay, every IP address that you see consists actually of 2 logical parts. One part identifies is a prefix. Some parts in the beginning identifies the network that it belongs to. So now we'll talk about a little bit about a network. Okay, not the LAN kind of network, because that deals with MAC IDs, Ethernet IDs. We'll see what a network means here. Okay, and then the remaining part is the host ID within the network. So any IP address that you see, okay, for your machine, okay, like, you know, your desktop, etc., whatever, okay, logically it is actually of 2 parts. There's an initial prefix part which identifies which network does this thing belongs to, and then there is a last suffix part which says within that network the ID of this particular host is this. These 2 together is actually a IP address. So we'll come back to this in again and again. So if you look at all addresses out there, okay, at the very beginning you had what are called classful addresses. So when internet started, all addresses, so this 32-bit quantity, so all zeros to all ones, so many patterns, each of them can be an IP address. Okay, so people wanted IP addresses. So you see, you can be an organization. As I said, there is a network part. Okay, there is a network part and there is a host part. And the idea was to give this, if some organization wants a block of IP for assigning to its machines, okay, give it 1 or more networks and then let that organization assign the host part. So just telling that, okay, the top bits that you can use is this. I fixed it. You have to use only 1101.0.0.1.0. Okay, so every machine that you have, the top bits can be only this. but then the remaining 24 bits are free to you. So then the organization can, as per its requirement, assign machines whenever new machines get organized and so on. But you are guaranteed that all machines in that organization will have the top 8 bits like this. Which means if another organization I give 1001, let's say 0010, so this one bit is different, and then it assigns in whatever way it wants to assign the next 24 bits for its machines. Okay, I'm guaranteed that any machine in this organization and any machine in this organization, the IP address is going to be different, which is what I want. I want the IP addresses of any two machines in the world to be different. It's kind of a unique address. And again, when I say machines here, I basically means the network card assigned to the network card. Okay, so originally to classify these network parts, okay, the internet again authority, I'll talk about that also, which is the authority, said that all addresses I will break up into these 5 classes. Okay, B and D will not worry about. Okay, these are the 3 things that are actually the host addresses that we assign. This is a class A, class B, and class C. So you can ask for a class A address or a class B address or a class C address. That's it. Okay, so if you're an organization asking the internet authority for IP addresses, you say I want 3 class C addresses. I want 1 class A address. Okay, and what are they? So this picture will make it more clear. For class A, top bit has to be 0, and then this is the network part, and the remaining 24 bits is the host part. Okay, that means the total number of class A networks that can exist is 127, 7 bit to the power 7 minus 1. All zeros is not used. Okay, and then number of hosts can be, again, let's put a question mark. Right now, just think 2 to the power 24. This -1 and -2, put a question mark. After we come back from the exams, I will recapitulate a little bit and then I will talk. But I need to talk about something more before I talk about -1 and -2. But the simple thing is, you can have 2 to the power 24 hosts because that's the number of bits that can change. Okay, class B 10, but then more networks. So you have 2 to the power 14 bits networks and then 2 to the power 16 hosts. Okay, again, forget about the -1, -2. Class C, again, top 3 bits must be 110, network, only very few. Okay, this just the way it is interpreted. Okay, and we'll see that is a that is a relationship with routing later on. So if you think for a second, okay, so this entire space of 32 bits, all zeros to all ones. Okay, somebody has said you can have only 127 class A addresses, class A networks, only this many class B networks, and this many class C networks. This seems like a large number, but this number is not very large, given that you have billions of things that need IP addresses. And I'll discuss some more as to what we do about them. But right now, just understand the very basics. We'll come back on the exam and do the remaining thing. Okay. So the idea was this. So there is an internet authority for assigning IP addresses. So if you have machines that you want to connect to the internet, you will need IP addresses for them. Somehow that authority has to ensure that any 2 IP addresses in the world need to be unique. So how do they do that? They said that I will give you a network address. I'll give you only the top bits. And the way I will give you is, you tell me that how many hosts you need. Fine, you need only, so this host is only 254 hosts. You need a connection of maximum 200 hosts. I'll give you 1 class C address. If you say 1000 hosts, I'll give you 4 class C addresses. Okay. If you say 10,000 hosts, I will probably give you 1 class B address. I can also give you so many class C addresses. Okay, but something that fits your requirement. So by saying that I will give you a class C address or I will give you a class B address, what I say is, I will fix this part of the thing when I give to the organization. then the organization fix this, and this. If I give a class, then the organization is free to change whatever it does in the host part. So that kind of guarantees that any two machines in two different organizations. So within an organization, they will be different. That's the organization's responsibility. And then any two machines in different organizations obviously will be different because the network part assigned to them by the central authority is different. Is this clear? This notion of class A, class B, class C? Yes, no? How many people do we have in the class now? Okay, we have 14 people. Still enough to answer. Is this okay? What is class A, class B, class C?
Yes, sir.
Okay, good. So that's how things were assigned earlier. Okay. And then how do I specify this? We'll come to this. So this, as I said, the network will specify as saying WX, Y dot Z. Look at this example. Okay. So this slash notation basically says I will put an IP address. So when I just say an IP address, you do not know whether I'm specifying a network or an actual host. Okay. When you say this slash this is saying first this many bits, or sorry, last this many bits are available to you for the host part. I'm sorry. First this many bits are available to you for the network part. So /8 is a class A network because the top 8 bits are the network part. You have the remaining 24 parts as it is. Okay. So typically the parts that I can change, I put a all 0. It's not necessary. But even if I put something else, it don't have any meaning for the network. Okay. So when I just put 64.0.1.0, I do not know what this is. Okay. This is an IP address basically, just an IP address. So this can be something assigned to a host also. Okay. But when I write it into this notation, /8, this basically says the top 8 bits define the network. The remaining 24 bits can be anything. So 0, 1, this 1 has no meaning in this case. Okay. This basically says 24 bits is for you to send. So that's why we don't specify 1. When we specify a network, okay, the top parts that is relevant we specify. The remaining parts that are there, we don't specify. So this is /8 says top 8 bits on network, /16 says top 16 bits on network, /24 says top 24 bits on network. We'll use this notation again and again shortly. May not be today, we'll see. And then we'll come to know it. Okay. So here are some, let me see if I want to do this now. Let me not do it now. Okay, we'll come back to this. Now, so this was the original internet. Class A, class B, class. Okay. Now you see, the problem was this. IP block allocation, as I said, were done by class. When some organization wanted some IP addresses, they were given either an entire class A or entire class B or entire class C. There were some policies and all, okay? But you get only multiples of class A, class B, and class. Okay? But that's a wastage of IP address. An organization may not need a full class. For example, think of a class A. You have 24 bits to assign hosts. That means you have 2 to the power 24 machines that you can assign IP address to. That's a very large number. Okay. But not that many organizations will need that. When I come back from the lab, someday I will show you kind of some of the organizations that have class A addresses. And you will see very funny things. You will see large organizations like IBM and all, which were like behemoth organizations in those days. And you will see very strange companies that have, that you don't normally think as using that many computers in those days, basically. Okay. But see, the IP space is bounded. You have ultimately 2 to the power 32 variations of 32 bits. Now, old days, it was not a problem. It was not a problem because not that many machines were there on the internet. So 2 to the power 32 seemed like a very large number. So if somebody wanted, says, oh, I want 30,000 addresses. I'm a large organized corporation. I'm going for computerization. I want 30,000 addresses. You said, let him have a class. Somebody said 100,000 things in the next 10 years. Let him have a class. Okay. But then if they don't do that, then the space gets wasted. And anyway, you can only do multiples of class A, class B, and class C. Okay. So just think of somebody wanting 300 addresses. So one class C, which is maximum 254 addresses, does not suffice. So you have to give at least 2 class Cs. But then the multiple becomes 254 into 2. That is more than 500. And you're wasting some 200 address spaces, which will never be used. But nobody else can use it. Because then there will be a problem of IP conflict. 2 machines may have the same IP address. My goal is to kind of ensure that any 2 machines in the net has different IP addresses. Okay. So nobody envisages that our internet will kind of explode like this. So they kind of thought classful addressing is fine. But then it is exploded, okay, and more and more machines started, need for the IP address grew. Okay, people started thinking that you cannot do that. You cannot waste this IP address space because you may run out of IP addresses eventually. We'll see that we did something else for that, but definitely classful addressing seemed bad even in the early days. Right after some time when you started seeing the growth of the thing. So what is done now is what is called classless addressing. We still have left terminologies class A, class B, class C. We'll see them used. Okay, you still you can ask for class C addresses and so on. But what you get always is no well-defined class. Okay, so no fixed size prefix for the network part. You choose the prefix as per need, and you allocate only what is needed. So that value of P, the number of bits that define the network part, the prefix initial number P in bits, can be arbitrary. So here is an example. Suppose an organization needs only 56 IP addresses. So with a classful addressing, you have to give the minimum you can give is 1 class C. Okay. If you do that, around 200 addresses gets wasted. This organization is a small one, it will never need more than 56. It says I will maximum need for 56. Okay. So classful, you have to assign a whole class. Let's say assign I this one. So this /24, that means 24 network bits, okay, 8 host bits. So this is the part that is defining my network. It wastes around 200 addresses. Okay. What I did with this classless is this. I changed this to 26. Understand it carefully. This is 26 network bits, 6 host bits. Because 6 is 2 to the power 6, 64 enough to do this. So this will have 200 into 100 all IP addresses, 200 dot 2 more bits. Out of those 8 bits, 2 more bits, and these are 0, 0, 0, 0, and then these 6 bits you can organize to your 56 machines. But all your addresses must start with 200, 100, 200, and then 0, 0 in this last part. Okay, which means now the remaining 192 addresses in this block, I can say I can give to some other organization which will say 0, 1 and then 6 bits. Okay. Now what is 0, 1? So 0, 1 all zeros, okay, is 2 to the power 128. Sorry, 2 to the power, so that is 128. Okay. So basically I have created 2 networks now. 200, 100, 200, 0 /26 and 200, 100, 200, 128 /26. The same manner now, the remaining things I can have 1, 0 and 1, 1. So I can create 200, 100, 192, sorry, 200, 192.192/26. Okay. Sorry, there is a 01 is not 128, right? 01 is 64. Okay. So 10 is the 128, 11 is the 192. You see how this 0, 128, 192, this number came. So sorry. So the one that we had earlier done is 200.64/26. Okay. So I've kind of broken up this 200. Sorry, not 2. So there's a lot of problems out here. So this 220, 220. So this thing I'll cut. Do you understand? This is just a type. Okay. So I earlier had the 200, 100, 200.0/24, one net. I've broken this up by borrowing from the host part, saying that no, this you don't need that many hosts. So you will use the 8 bit, but the top 2 bits of you will always be 0. So you can only change 6 bits. That means you can maximum have 64 addresses. Then I go to the other organization when they want, somebody else wants another 50 bits, 50 machines. I say you can only have that, but then top bits must be 01. That means 64 bits. Then somebody comes in, I say, oh, you have another one with less than 64 requirement. I have 10. Similarly, 1. And I specify how many bits is the network by specifying this 26, which is saying this 888 plus 2. So when I get an address 200.100. Let's say 128.32, and I know by some means that 26 bits is the address. I know that to break up the first 26 bits as the network, and that network will always have 10. These first 3 things, and then this 10 in the fourth one, and then this 32 will basically become there. Basically, this is, I'm writing wrong. This will be 200 dot something. 32 will come in the first block. So this was a little bad, okay? But you get the idea. So the one class C that I would have given to one organization, which would have used only 56 and wasted around 200, now I can give it to different organizations, 4 different organizations, because other organization will come back with similar needs. If somebody needs more than 200, then I will give it something more. I may borrow from the top 24 bits now. You can break it up. I can break a class B address now. Okay. Are you with me? What is classless addressing? Yes, no? So this is the last thing we'll stop here. Okay. So who is this central authority? So how is IP address allocations done nowadays? Okay. So the top authority controlling this called IANA, Internet Assigned Numbers Authority. You can go to this site to take a look at it. But you don't go as an organization, you don't go and request IANA for IP addresses. What you do is you go to what is called regional internet registries. And there are regional, SAFRINIC is for Africa, APNIC is for Asia Pacific, LACNIC is for Latin America and Caribbean, ARIN is I think for Europe, RIPE is for US, North America basically, and so on. Okay. So you have this entire IP pool. Okay. Then this is with IANA. Then IANA gives a chunk to each of these areas. Okay, kind of contiguous chunks. Okay. Now people have realized IPv4 is a precious resource. So you cannot just ask for it and get it. So if IIT Kharagpur has to get it, okay, it's actually very, very not complex, but So typically it's not given to end users freely. So let's say now, let's say this is my app link. This is the Asia Pacific link. So ISPs in the Asia Pacific region will again ask for it. So maybe BSNL will ask for it and get something. Singtel, which is Singapore's network, will ask for it and something, and same for Airtel, etc. Now, when you take a connection from BSNL, okay, you can ask BSNL to give me 5 IP addresses. So that's normally how it works. Okay. And why this is done, you will understand a little later. This region and ISP based allocations keep IP address blocks in a region mostly contiguous. Okay. So the entire block, let's say IANA says 000 to 000 something goes to Afrin. Then the next contiguous some block goes to happening. They have some policies, there are no demands and so on and so forth. Okay. They reallocate and everything. So that's not a very simple process, but what happening gets is mostly some contiguous blocks. And then when BSNL asks for it, it'll give a chunk of that to BSNL. Again, there are policies and everything. It's not that whatever you ask for, you get it. You have to pay for it and so on. Okay. So the chunk that BSNL gets is also kind of contiguous. And then BSNL will divide it among its customers in certain way. Why this contiguous things helps in routing, we'll discuss that later on. Okay. So as IIT Kharagpur, for example, so we have a RailTel, we have RailTel as a ISP. So RailTel will have a chunk, we'll ask RailTel, RailTel will give us some IPs. But then I can also ask AppLink. You have to fill up a form, you have to justify why you need it and so on. A small number of IPs you can also get directly from it, if they approve. So we have, I forgot, old days it is 7, 8 class C addresses. So it's not that you always want classless addresses. Okay, if you have sufficient needs, you can approve, you can get a class C. So almost class A and class B are almost never allocated, to the best of my knowledge. So that's like too huge and nobody wants it in one go, and that will be a wastage. So I don't know the exact policies, but to the best of my knowledge, class A and class B are no longer directly allocated. It's just broken up like this, given to ISPs and all, not directly allocated to end customers ever. But class Cs you can get, or you can get even a smaller network directly if you want. But then if you want, is not as free as that. If you want it, you get it. There's a lot of policies. You have to apply, you have to justify. Of course, you have to pay. Okay, payment is a smaller thing actually. Many people are willing to. And then based on need, they will approve basically. But most often, what you get is through your ISPs. Okay? But then that brings us to a question, and we'll end the class with that. Okay, that see in IIT Kharagpur, we have what around normal 11,000 students, another nearly 700-800 faculty, their families, staff, okay, and many people have multiple machines, etc. Right? So we have like 20,000 plus machines running. So 20,000 plus machines running at one time. If you have to have unique IPs, okay, then that requires 20,000 IPs. So that will require a class B or so many classes or very large network. But as I said, RailTel will probably give us, I don't know what the current thing is, but I will tell you some old days data with BSNL and all. And they will give you 4 IPs, 8 IPs. You will haggle for giving 16 IPs, 20 IPs, and so on. Okay. And then we purchase IPs separately. We got like 8 class C addresses. So that's what, like 2,000 plus addresses. But my goal is to keep everything unique in the entire world. So there is a question as to how do you manage to run 20,000 machines with only 2,000 IPs? Because what we have learned so far that every machine needs to have a unique IP. So how do you assign 2,000 IPs to 20,000 machines, they're all communicating at the same time, okay, and make it unique. So that's a question that you probably will not be able to answer fully, but I request you to remember this question, write it down maybe, and we'll come back to it later on. Okay, any ideas? Anybody? What do you think happens? You get the problem, right? I'm telling you, IIT Kharagpur does, just suppose, unless they've got something recently, around 2,000 IPs. So how do 11,000 students machines run with only 2,000 IPs? Based on your ad hoc knowledge of, and many of you do a lot of things on the side, very, very good things. Do any of you have any clue? Any keywords that make it work? No? How many people do we have left? We still have 13. Good that it is recorded, so people can listen to it. You heard the term public IP, private IP? So these 2,000 IPs that I'm talking about is a public IP. So IP space has become scarce. Okay, so just a bit of history. So for a long time, since late 90s, early 2000, people were very scared that IPv4 will run out of space. Okay, so IPv6 came in. If you're as old as us and following these things in early 2000, it was like a doomsday thing. It'll run out in 5 years, it'll run out in 6 years, it'll run out in 4 years. A lot of studies and so on estimating when it will run out and so on. And then you will have machines and no IP addresses. So IPv6 came into being, okay, which expanded this 32-bit address to 128-bit addresses. And that seemed to be too high. And then the forecast in those days was that IPv6 will take over the world. Okay. So eventually, after this, everything will become IPv6. The problem is basically that, but that has not happened. There's a lot of IPv6 machines, lots of them. I'll give you some statistics near the end of the course. But it's not that the internet. See, for example, here in IIT Kharagpur, we don't have a single IPv6 machine problem. I will not say single, okay, but I don't know. I should not make that tall a claim, but almost everything that I know that we run is IPv4. Okay. That has not happened. So there were 3 different directions in which people went to kind of make sure that I have sufficient IPv4 space. One was this that we are just discussing. Reduce wastage. That happened long ago. Okay. So do classless addressing, only allocate what is needed, more strict policies, you don't just ask and get and so on. But you people will need it, so you still give. One is to reduce the wastage of the IPv4 space. One is IPv6, okay, and have a larger address space. Okay. But after we do IP and all, we'll see whatever the problems there basically. Okay. And the third is basically, which was always there, okay, but utilization of more of that is this notion of private IP and public IP. And then translating between them. Okay. So we will, kind of, let me do one thing. No, let's not do that. So after we do IPv4, understand IPv4 properly, I'll discuss this a little bit. Okay, so we'll end here. Hardly anybody. Thank you for attending the class. So basically know what an IP address is, know this different logical division between network and host part, and what is classful, what is wrong with it, what is classless, how can we assign a classless address. Okay. We'll stop here and then we'll start with IP subnetting, then we come back. The special addresses are easy to look at, we'll see. So we'll stop here. Thank you for your time. And if you have any questions regarding this exam, anything, I am here. You can always ask me over email also. Otherwise, you can leave. Class is over.